Swayam Prabha. Digital India. Educated India.
सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be lecture number 34 on the series on mechanical measurements. In the last two lectures we have been looking at the measurement of flow, and we will continue with that. Towards the end of the last lecture, that is lecture number 33, we are looking at an example involving the measurement of flow by use of a venturi. That was example 38, and we will continue with that because we were not able to complete that example in the last lecture. We will also be comparing for the same set of flow conditions what will be the performance of the venturi, which of course is a part of example 38. How does it compare with the case of a nozzle, and how does it compare with an orifice plate if the venturi is replaced by either a nozzle or an orifice plate. Subsequently, we will look at an important flow meter which is very commonly employed. It is called the drag effect flow meter. It is also named as the rotameter. It is very common in industrial practice and in process applications. So, we will look at that, and we will round off the discussion on the drag effect flow meter by taking an example and working out the characteristic of such a meter. Subsequently, we will look at other types of flow meters, including what we earlier called as the positive displacement type flow meters, and some other flow meters which cannot be classified in one way or the other. We will look at them also if the time permits. To recapitulate, example 38 consisted of a venturi to be used to measure the flow of air at 5 bars and 25 degrees Celsius. The maximum flow rate is 1 kilogram per second, the minimum flow rate is 0.3. We have to determine the size of the venturi such that the pipe Reynolds number is not less than 100,000. In fact, we did that part of the problem in the last lecture, and we also have to calculate the differential pressure developed across the venturi if beta equal to 0.6 for both the cases, that is 0.3 kg per second as well as 1 kilogram per second. That is what we want to do. So, we will go back to our board on which we had looked at some of the numbers, and what I have done is I have taken the material from the previous lecture. The Reynolds number based on the diameter is given by the formula is 4 times m dot minimum divided by pi d into mu, where mu is the dynamic viscosity of the air at the pressure and temperature which is specified. So, all I have to do is to substitute and solve for d, because the Reynolds number is given as a limiting value of 10 to the power 5. So, I will take 10 to the power 5 equal to 4 into minimum mass flow rate is 0.3 divided by pi divided by d is the diameter which is to be determined, multiplied by mu is 18.4 into 10 minus 6. So, I solve for d and I get a value of 0.207 meters, that is about 20 centimeters the diameter of the pipe. The value of beta, which is the ratio of the diameter of the venturi at the smallest area region and the pipe diameter, d by d is given as 0.6, and therefore I can calculate d as 0.6 times 0.207, which is 0.124 meters. So, the proportions of the venturi required for this particular measurement is decided based on the Reynolds number which is specified to have a minimum value. And at a Reynolds number at 10 to the power of 5, you remember that we had given a figure which gave the value of the coefficient of discharge as a function of Reynolds number, and from that we take the value of C equal to 0.977, and the value of m, the approach velocity of approach factor, is 1 over square root of 1 minus beta to the power of 4. It is 1 divided by square root of 1 minus 0.6 to the power of 4. It is 1.072. Now all I have to do is to use the equation number 6 in the previous lecture. With y equal to 1, we are assuming that there is no expansion or there is no compressibility effect. We calculate the throat area or the area of the smallest section as pi small d squared by 4, which comes out to be 0.012 square meters, and d is 0.124, which was determined in the previous slide, 0.0124. So the delta P developed by the Venturi when the Reynolds number has the minimum value of 10 to the power of 5 corresponding to a mass flow rate of 0.3 kg per second is given by this formula, m dot minimum divided by Cm into EAT whole square divided by 2 rho. This is the formula. This is actually the obtained from the characteristic of the Venturi, and we have already determined C, m is already determined. All I have to do is to plug all those values. So m dot is 0.3, C is 0.977, m is 1.072, and EAT is 0.012. That is what is calculated here. That whole square divided by 1 over 2 into 5.844. This is the density of the fluid. So you get a 47.4 pascals. This is the pressure head, which is the pressure difference across the Venturi for the minimum mass flow rate. In fact, we can see very easily that for the maximum mass flow rate, all I have to do is to change this m dot to the value equal to 1 kg per second, and I have also got to determine the value of C appropriate to the Reynolds number corresponding to the maximum flow rate. And if you remember, the mass flow rate and the Reynolds number are really linearly related, which you can see from the formula here. Reynolds number equal to 4 times mass flow rate divided by pi into d into mu. So everything else is fixed here, only m dot is now changed from 0.3 kg per second to 1 kg per second. So Reynolds number will be larger by a ratio of 0.1 to 0.3, 1 over 0.3 of the 10 to the power of 5. That is about 3.3 into 10 to the power of 5. So the Reynolds number increases, and correspondingly the value of the coefficient of discharge also changes, and the value we can take from the same graph. The value of C turns out to be 0.984 from the graph. So we will just mention here from the graph. This corresponds to Reynolds number 1 over 0.3 times 10 to the power of 5, corresponding to this is the maximum value in this particular application. This is 3.3 recurring in 10 to the power of 5, and corresponding to that, this is the value of C which I am going to get. And all I have to do is to now substitute this value of C and the corresponding value of the mass flow rate in the formula which we used earlier. Here all I have to do is to replace this by 1. So we will say instead of minimum, I am going to replace it by maximum value, and the value of C by the value which I just now wrote down. So C will be equal to 0.984 corresponding to the new value of C, and the m dot maximum will be equal to 1 kg per second. So all I have to do is to substitute these values, and the value of delta P will be obtained. This we can call as a maximum delta P obtained using this particular Venturi, and this will be 1 kg per second divided by 0.984 multiplied by 1.072, that is the velocity of approach factor, multiplied by 0.012 is the area of the Venturi at the smallest section, whole square into 1 over 2 into 5.844, which is the density of the fluid. So this is the pressure difference which is developed, which is equal to 519.2 pascals. Actually, I can convert it to a more useful unit in terms of millimeters of water. All I have to do is to divide it by, assuming the water density is 1000, which is a good enough approximation for this problem. It will be, you simply divide by G, you simply divide this by G, which is 9.81. So this can be converted into millimeters of water. It will be 52.9 millimeters of water. You divide by 9.81, that comes to that. So this is the pressure drop or pressure difference between the inlet and the smallest diameter section of the venturi, which is what is measured by the manometer. So 52.9 millimeters of water is what we are going to get. Now let us look at what is going to happen if I do the following. So what I am going to do is the following. I am having the venturi. This is the first case which we did. So I want to compare with the case of a nozzle. So this is venturi, this is the nozzle, and I have the orifice plate all having the same value of beta in each case. So what I have to do is to work out the appropriate values of C for the case of nozzle and C for the orifice plate. That is the only thing which is going to change, because all other conditions are given to be the same, that is the same mass flow rate and the same diameter of the pipe, because we have already determined the diameter of the pipe such that the pipe Reynolds number is not less than 10 to the power of 5. So we are going to specify these as these conditions as being fixed, and I want to compare the venturi, the nozzle and the orifice plate. This I have worked out, and I will show you on the slide. So the mass flow of air is 1 kg per second and 5 bars and 20 degrees Celsius. That is the inlet pressure and temperature. The pipe diameter is 0.207 as determined in the earlier case, and the beta value is 0.6. These are held fixed. The corresponding velocity of approach factor is also 1.072. All these are fixed for all the three cases. So the performance of a venturi, long nozzle, orifice plate with corner taps are compared in the table given in the next slide. What is going to happen is that the value of C is different for the three cases, and therefore to that extent there will be changes in the performance. So if I look at the comparison of the venturi, nozzle and orifice, the values of C are determined, and in fact you remember in the example 38 I had 0.984. For the nozzle I use the appropriate expression which was given in the earlier lecture. So this works out to be 0.988. For the orifice it comes to 0.605. These three cases correspond to Reynolds number equal to 3.33 recurring multiplied with 10 to the power of 5. This is for the highest mass flow rate case. The corresponding values of K, the flow coefficient, can also be calculated, nothing but C multiplied by the M. M value is the same for these three cases, equal to 1.072. So this comes to 1.055, 059, 0.649. We see that the value of K is the smallest for the orifice, and for the venturi and the nozzle they are more or less the same order of magnitude, same magnitude, very close to each other, and therefore we expect the delta P generated by both the venturi and nozzle to be close to each other. You can see that 519.2, which was worked out in the example 8 to 38, and 515.2 for the nozzle, slightly lower because the value of K is slightly higher, and for the orifice you get the highest value of 1372 pascals. In fact, I convert this to millimeters of water as I indicated. Simply you have to divide by 9.81 and you get 52.9 for the case of venturi, 52.5 case for the case of nozzle, and 139.8 for the orifice plate. So the orifice plate indeed gives you the biggest measurable effect of delta P. That means that it is the most sensitive in terms of the amount of pressure drop you are going to get for a given condition. but as I mentioned in the last lecture, the penalty will be that we are going to lose most of this 139.8 millimeters of water pressure drop will not be recovered, most of it is going to be dissipated. In the case of Venturi, of course, 52.9, only a few percentage of this will be lost and most of it will be recovered. That means that the pressure at the end of the expansion portion, where the diameter changes back from the smaller diameter to the pipe diameter, the value will be more or less equal to the pressure earlier. That means that the pressure drop is the penalty which we are going to pay in this case. I also mentioned in the last lecture that the Venturi requires the longest length for the installation, nozzle next to that, and orifice requires the least amount of length for the installation. That means that from the point of view of installation, all we need is two flanges and we can put the orifice plate, whereas in the case of Venturi and nozzle we require some more sophisticated arrangement, certain length has to be introduced and so on. The other point I would like to talk about before we leave this topic is to look at how a typical installation will be. So, the typical installation of any of these types of flow meters, what does it require? For example, if you have any of the flow meters, I will just put it in the form of a box. This is the flow meter. It requires a straight length of tube upstream of the flow meter, very important. It requires a certain length of the pipe which should be straight. I cannot have a corner or a bend in the pipe, because when there is a bend, the flow becomes somewhat disturbed from its parallel type of flow arrangement. For example, if I have a bend like this, there will be secondary flow and the flow will be disturbed here. There is this disturbed flow. Therefore, we should avoid putting the flow meter right next to a bend where very close to the bend. So, we require maybe 20 to 50 diameters of the pipe are required, or maybe more depending on the installation. Similarly, we require a certain straight length of tube downstream of the meter. If we do not want to have any effect of the downstream and the upstream, we need some straight lengths both before and after the flow meter. The flow meter itself is now either one of the three we have. It may be an orifice plate, which of course will be smallest in terms of the length. The nozzle will be slightly longer, and eventually of course it will be a very long installation. The length of the Venturi is the longest of the three. The other point I would like to talk about is what is done normally is, if you are measuring if you take the Venturi for example, so this is typically the Venturi. So, you are going to measure the pressure difference between these 2 points. This is delta P what I am going to measure. So, normally what is done is you have several taps on the periphery. So, you have the pipe here, I have taps. So, this is the pipe thickness, I have several taps. That means that the pressure, they are all communicated to the same and that means that I am going to measure the average of the pressure in the 4 taps, in this case 4 or more than 4. So, if you look at the cross section of the pipe, the pressure taps will be there like that, and on the wall here, on the periphery, all of them are connected to the same port or the same hole, which is going to be connected to one arm of the pressure difference measuring device. So, here also you will have several holes on the periphery, all of them connected to this tap, and here I have several holes which are connected to this tap. So, it is the average pressure around the periphery which is normally measured in the case of an installation like this. So, with this we have finished looking at the variable area devices, and just to recapitulate, variable area devices are going to deliberately introduce a change in the area of cross section, which will affect the velocity of the flow, and the kinetic energy is converted to potential energy in the form of pressure head, and what is measured is the pressure difference between two chosen stations or sections along the length of the installation. So, let us now look at what are the other kinds of instruments which can be used for measuring the flow rate. One of them is called the rotometer, or it is also called the drag effect meter. So, we will look at the principle of operation of a rotometer, how it is constructed, what are its characteristics. We will derive what is called the rotometer equation, and then we will look at the design considerations, and then we will take up an example 39. That is what we want to do. So, just I have shown a schematic of a rotometer, so that we can take off from this. So, essentially what it has is a vertical taper tube. It is a vertical taper tube. The direction of gravity is from top to bottom. Okay, it has to be aligned vertically on the with respect to the local plane. For example, if you are having a tabletop experiment, the tabletop is supposed to be horizontal, the rotometer must be exactly vertical to that plane, to the horizontal plane at the local place where we are making the measurement. The rotometer must be exactly vertical. In the case of the three measuring meters which we talked about, the venturi, the nozzle and the orifice plate, normally we use the horizontal orientation. The meter will be located horizontally in the pipeline, and many times the pipeline is actually horizontal, and therefore it does not involve any problem. But if you are going to install a rotometer, you have to make an arrangement such that locally the flow direction is exactly vertical from bottom to up. It should be from bottom to top. The flow direction is fixed from the bottom to top against the gravity. Very important to remember. So, let us look at the schematic of the rotometer. Essentially it consists of what is called a bob. Bob is this piece of material which I have shown in the form of a cylinder with a small cap onto it. The diameter of the bob is this d, and it is normally equal to the diameter at the bottom of the tapered tube. Of course, here I have shown the taper to be very exaggeratedly very high. Actually, the taper is very small, and we may not even be able to, by looking at it, we may not be able to say that it is a taper tube. It is a very small taper we are talking about. So, how does it work? Just imagine that the bob is in some location, and this location is measured from the bottom here. So, y is measured in this direction from here. So, the bob is some location. So, you can take this position as the corresponding y. Okay. So, now suppose there is a flow of fluid, it may be either a gas or a liquid. If it is flowing like this, it has to negotiate the bob, go around the bob like this between the space available between the bob and the outer tube. The area available for flow is actually the annular area between this d and the local diameter of the outer tube. There is an annulus which is formed. Okay. So, the velocity, if we say the value of the velocity is um in that annular region, the bob is going to experience 2-3 forces. One, of course, it is the weight of the bob which is vertically downwards. Then there is the force of the buoyancy, because it is displaying a certain volume of the material which is flowing, either a gas or a liquid, and therefore there is a buoyancy force which is upwards, okay, by Archimedes principle. And thirdly, there is a drag force which is because of the flowing fluid which is negotiating over that and is flowing and joining here. So, it flows with a larger velocity in the annular region and goes back and joins here. So, because of the form of this particular bob material and because of the flow which negotiates it and joins at the back, there is something called the form drag. The form drag is because of the subtle changes in the pressure acting on the surface of the bob, and this usually is written in the form of a drag coefficient multiplied by the kinetic energy of the fluid per unit mass. So, three forces, these three forces are going to now be in balance for a particular value of the flow rate. You see here that if the flow rate is in this direction, if the value of um is, we will see later that um is going to be a constant value, because the drag force, the weight of the bob and the force due to buoyancy, these must be always in balance, okay? And this will be for a given value of um. The um gets fixed because of that, and what is changing here is only the area available for flow, that is the area in this annular area surrounding the bob, that is the area available for the flow. So, actually what is happening in this case is that the area is changing, and we will see little later that more or less it is a linear change in area. If the taper is small, the change in area is linear, and therefore the volumetric flow rate which we infer from the position of the bob is a linear function of the position of the bob from the datum which is here, okay. So, let us now look at the way this turns out. So, I am going to work it out on the, so we want to look at the rotameter equation. We will actually derive this equation. So, let me just make a simple sketch here again. This is the tapered tube, and let us say this is the axis, and the gravity force is acting in the downward direction like this. The flow is taking place from below, and here is the bob. We will say that is rho b is the density and the volume is Vb. So, this is density and this is the volume of the bob. So, density and the volume, and in fact you can see that the weight of the bob will be nothing but rho b Vb multiplied by g, the acceleration due to gravity at the location where we are doing the experiment or where you have set up the rotameter. So, this is one force which is to be taken into account. What are the other two forces? I have already talked about. So, the force of buoyancy, this will be equal to rho f into Vb into g. It is the weight of the displaced fluid whose volume is equal to the volume of the bob. So, if the density rho f is the fluid density, Vb is of course the volume of the bob, multiplied by g gives you the second force. It is actually upwards and this is downwards. Okay. There is a third force which we called as the drag force, and most certainly it is not due to viscous effects, it is only due to the shape of the way the flow negotiates the body, and therefore, it is mostly due to the form of the object, therefore, it is called the form drag. This drag force we will call it as Fd is equal to some coefficient Cd times the kinetic energy of the fluid, which is given by density into um squared by 2, all for unit volume. That is what we have done. So, this force is also in the upward direction. So, what do we need to do now? The force acting in the downward direction must be exactly balanced by the sum of the forces acting in the upward direction. That means that I have to equate 1 to the sum of the two forces which are given by 2 and 3. So, we can say for equilibrium the downward force this is a weight must be the sum of the drag force, drag and the buoyancy force. The two forces which are acting in the upward direction must be equal to W, and therefore we can just do that. So rho B VB into G, this is the weight of the bob, must be balanced by the buoyancy force rho F VB multiplied by G plus the drag force, which is now given equal to CD. I think I left out this AB, I will just go back to that and explain to you. Rho F UM squared by 2, let me go back and make that correction. This is proportional to CD multiplied by the area which is intercepted by the flow, that will be the frontal area of the bob material. So AB is the frontal area of the bob. So this is the equation, and I can solve for UM. You can solve for UM, and you can rearrange like this. So UM equal to this minus this, and then you appropriately divide, and UM squared is here, therefore I am going to get a square root. So this will be 2G VB is common to both these two cases, multiplied by rho B minus rho F divided by rho F CD AB. So the value of the velocity UM is equal to this. So what does it mean? It means that the velocity cannot change, whatever may be the position of the bob, equilibrium requires that the UM is a constant. That means if I am allowing certain amount of fluid to flow through the system, it will decide the position along the length of the taper tube, where the value of the velocity in the annular region between the bob and the outer tube will be exactly equal to UM. So the equilibrium position will be determined by the requirement that the velocity UM be a constant given by this particular quantity, assuming that CD is a constant. So normally what is done is that the CD is dependent on the shape of the bob and so on. So normally it is the design of the bob is such that the CD is more or less constant for the range of operation of the particular rotometer. Secondly, the density of the bob and the density of the fluid both are going to come into the picture. So the density of the bob does not change when you use the rotometer for measuring the flow rate of one fluid and another fluid. So rho F is going to change. That means that the calibration is dependent on the fluid which is being used. So normally what is done is that it is calibrated for a particular fluid, and if the density of the fluid is different, we will have to use a correction factor for that. For example, if you use air at one particular pressure and temperature, and if the temperature changes, the density of air will change, therefore rho F will be different, so you have to correct for that. That means that the rotometer calibration is dependent on the fluid and its temperature in the case of gases, so that you have to take into account some of these things during the operation of the thing. Now that we have got the UM, and let us look at what is the flow rate. So volume flow rate is given by the velocity times the area available for the flow. So UM into A available for the flow. Okay, it is very simple. UM into F. UM already I have found is a constant given by some quantities which were dependent on the bob density, the fluid density, and the CD and the AB and so on, which are all fixed, and therefore only AF is going to vary. And let us look at AF now. Suppose we have a taper tube here and I have a bob like this diameter is D, the area available between here and here, okay. So I can say that is if the diameter, local diameter is D, which is a function of y, y is measured from the bottom from some datum d at y. I will say d at y is equal to, let us say, d plus some a y, where a is called the taper parameter. This is called the taper parameter. So, I can say that A of area for flow is pi by 4 into d at y whole squared minus d squared. That is just the area available here around the periphery of that circle. Okay, that is the annular area. So, d of y whole square, I can square this. So, d of y whole square is nothing but d squared plus 2 a d y plus a squared y squared, and I am assuming that a is small, which is small taper. I can ignore this, ignore this factor as being too small. If we ignore that, you see that d of y squared d squared plus 2 a d y, and this dy y squared minus d squared, this d squared will cancel. So, this whole thing can be rewritten by taking the difference between that and that as 2 a d times y, 2 a d multiplied by y into pi by 4 is equal to a f, and therefore, volumetric flow rate q is given by um already I had an expression 2 g v b into rho b minus rho f divided by rho f into c d a b. This is your multiplied by the pi by 4 into 2 a d y. Of course, this will cancel off with this 2, it will become 2. So, pi a d y divided by 2 multiplied by, this is actually the area. So, this is the area factor, this is the velocity factor, this is constant, and therefore, you can see this is also a constant, a is a constant, pi is a constant, 2 is a constant. So, I can say this is nothing but some c times y, where c is a gauge constant. So, basically the rotometer is a linear device where the volumetric flow rate is given by some constant times the position of the bob, which is noted down. Actually, what is done in practice, if we go back to the sketch here, along this tube a scale will be marked, which will give you the position of the bob. You can read off the position of the bob by looking at the, for example, you can look at this edge here and find out where it is, and that will be your position of the bob. The position of the bob is given by the edge of this thing here, and corresponding division on the outside will give you the height above the datum, above this particular position. So, that gives you the y. So, you actually measure only the y, the scale reading on the periphery of the taper tube, and from that you multiply by a constant capital C, which is called the gauge constant for the rotometer, and you have the volumetric flow rate. Rotometers are made for applications with gases and with liquids. They can span very large range of values for the volumetric as well as the mass flow rate. We have very small rotometers which use a bob made of cork or pith, some material with very low density, so that it can be used for gases, and it could be only a few millimeters in diameter and a few millimeters tall, to rotometers which may be a few centimeters diameter and maybe few almost half a meter length. So, depending on the flow rate, depending on the fluid, we can have different bob materials. The bob can be either hollow or solid to adjust the density to required extent, because the density, when we talk about the bob density, it is the average density of that bob. If you have a hole inside, the density comes down. So you can, by having a bob with a hollow inside, you can get a density which you want. And you will also see that if I go back to that equation, you have the Q equal to square root of 2G Vb into rho b minus rho f divided by rho f, and imagine rho b equal to twice rho f. If rho b equal to 2 rho f, we have rho b minus rho f divided by rho f, that will become 1. Then this becomes equal to 1. So the density of the bob, density of the fluid, both drop off, and it becomes a very simple expression. So this will be 1. So it will be 2G Vb by CD AB under square root of, that will be the value of C. Okay, this is a specific case where the density is taken equal to twice the density of the fluid, then the density term drops off from the equation. And in fact, it is found that even if the density of the fluid varies a few percent, maybe 5% or 10%, this is not going to alter the thing too much. The error is not very significant. The second point is that the taper parameter. If the taper parameter is not small, then you will have to, it becomes a straight nonlinearity will be there, and of course this can be taken care of by adjusting the scale on the side of the rotameter to include that nonlinearity in it. Therefore, when you take the reading, automatically it has been corrected for the slight nonlinearity if there is nonlinearity on it. So let us take an example so that we understand what is happening. So this example 39, I will work out on the board the numbers corresponding to this. A rotameter is to be designed for the particular conditions which are given here, to measure a maximum flow rate of 200 liters per minute of water at 27 degrees Celsius. This is the fluid whose volumetric flow rate I want to determine. 200 liters per minute is the maximum. The bob has a diameter of 15 millimeters and a volume of 3 milliliters, 3 centimeter cube, 3 cubic centimeters. The effective density of the bob is twice the density of water. This is what I said just now. If we take the density equal to twice the density of the fluid, then you do not have to worry about the density will not come into the picture. The total length of the rotameter tube is 150 millimeters, that means Y max, the maximum value, possible value of Y is 150 mm, and this must correspond to this 200 liters per minute. Y equal to 0 will correspond to 0 flow. When there is no flow, the bob will be at the bottom at its datum level, and when the full volume flow rate is there in the rotameter, it will go to the 15 centimeter or 150 millimeter level. That will be the maximum level possible for in this particular case. And the diameter of tube at inlet is also equal to 15 mm. So the bob will be just sitting, closing the opening at the bottom, and as soon as you start the flow, it will float up. When the flow is taking place, it will float up, and it will take a position which corresponds to the volumetric flow rate which we are measuring. So we want to determine the taper parameter. Tube taper is what is to be determined for a drag coefficient of 0.8. The drag coefficient is given to have a value of 0.8. So we want to find out what is the tube taper for this particular case. Let me work it out on the board again. So this is example 39. So the rotameter problem. The volume of the bob is given as 3 milliliters. Milliliter is 10 to the power of minus 6 cubic meter. I will convert everything to SI units so that there is no confusion in the numbers. And of course, we will assume G is 9.81 standard value. Vb is the volume of the bob, and then the diameter of the tube at the bottom, we will call it as, this is 15 millimeters, it will be 0.015 meter, and the diameter of the bob is also equal to that. This is also equal to bob diameter. That means to determine the frontal area AB, so we can determine the frontal area AB is the frontal area of the bob which comes in the calculation of the drag force. This frontal area will be pi d squared by 4. So, pi by 4 into 0.015 whole squared square meters, and this comes to 1.767 into 10 to the power of minus 4 square meters. So, the frontal area of the bob is fixed. So, we also are given the maximum flow rate. We will write it as Q max. It is given by 200 liters per minute. 200, 1 liter is again, this is 1 liter is 10 to the power of minus 3 factor will come in terms of cubic meters, divided by 60, because it is given liters per minute. I am calculating per second. So, this will be so many cubic meter per second. This comes to 3.33 into 10 to the power of minus 3 meter cube per second. That is the maximum volumetric flow rate. We are also given the value of CD to be 0.8, and we also know that Y maximum is equal to 150 millimeters, which is 0.15 meter. And if I go now to the equation which we derived earlier, we see that the taper parameter A can be solved for. The taper parameter is what we want to determine. This will be 2 into K, which is the gauge constant, divided by pi square root of, this can be done easily by going back to the rotameter equation and reworking the thing. So, CD AB, and I am assuming rho B equal to 2 rho F, and therefore, the density factor is this thing. And what is K? K into Y is equal to Q, that is the formula. Therefore, K into Y max equal to Q max. Therefore, K is nothing but Q max divided by Y max. Both of them are given, and the value of Q max by Y max comes out to 0.022. You put the Q max value and the Y max value, and you just work it out, it will come to 0.022. So, that value is known. All I have to do is to substitute all the values. This will be 2 into 0.022 divided by pi square root of 2 into 9.81 into 3 into 10 to the power of minus 6 is the volume, divided by CD is 0.8, and the frontal area is 1.767 into 10 to the power of minus 4, this whole thing under square root, and this works out to be 0.022. The taper parameter comes exactly equal to 0.022. Okay? And in fact, the taper parameter, if you remember, D at any Y value is equal to D plus A times Y. So, we can say D max is equal to D plus A times Y max, and all I have to do is to substitute. D is 0.015 plus 0.022 into 0.15 Y max, this comes to 0.0183 meter. So, the inner the diameter at entry. So, if you look at the rotameter tube, the diameter here is 15 millimeters, here it is 18.3 millimeters, and this length is 15 centimeters. So, this is designed for the rotameter. Inner diameter, entry diameter 15 millimeters, exit diameter 18.3 millimeters, the length of the taper tube is 15 centimeters, and the taper parameter is the value which we just described. Actually, you can work it out. The taper parameter will also mean this angle between the vertical, this angle you can give in terms of the angle. That angle turns out to be a very small angle actually, that will be 0.62 to 8 degrees. So, that angle, if I call it alpha, alpha is 0.63 degrees, a small angle for the taper. And in fact, if you were to calculate including the quadratic term, so the error in linearizing so we can calculate the error in linearizing for this particular instrument, that is given by a squared y max squared divided by d max squared into 100% as a percent of the area I can find out, and a squared y squared, this will give you about 3.23%. So, the nonlinearity from in the instrument is about 3%, which may be quite small for most applications we may have in mind. So, with this we come to the end of the discussion on a rotameter, and let us look at some other types of flow meters. The positive displacement meters, then I have got the vortex shedding type flow meter, and lastly the turbine flow meter. The positive displacement meters are characterized by, you have a device which is going to measure or which is going to send a measured flow, measured volume of the material from one side to the other side. So, what do I mean by that? For example, if you take a positive displacement type with lobed rotors, each rotation of this lobe, okay, a certain volume of the material is taken from the inlet and it is going to be sent to the outlet. So, this is rotating like this and this is rotating like this. Each time this rotates, it takes a certain volume of the material is taken from the inlet side and it is dumped to the outlet side. So, in this case, because we know the volume between the lobed rotor and the casing, if this volume is exactly known or measured accurately, then each rotation will correspond to one volume being taken from this side and taken to the outside by this lobe, and this lobe rotor will take exactly the same amount in the rotation. Therefore, by knowing the volume and the number of rotations performed per second, all I have to do is to measure the rotational speed of the rotor. I will be able to find out what is the volumetric flow rate, dividing the volume by the time it takes for this to be taken from this side to this side. So, this is positive displacement. That means that the amount of material coming from here is taken by the volume here and sent to the other side by what is called a positive displacement of the material. Another example which I have not shown here is, for example, a syringe. Most of you have looked at a syringe. Syringe has got a very accurately bored cylinder in which there is a piston, and if you advance the piston from one location to another location, an equivalent volume of the material will be going out of the syringe. A syringe can be coupled to a device which will push it by a push rod, and you can measure exactly how much volume has been displaced by looking at the reading on the cylinder of the piston of the syringe. You can actually look at the divisions and then find out what is the amount of material which has been dumped or which has been delivered. So, the syringe type of device is very often used in chemical instrumentation. When in instruments where you want to deliver a certain amount of fluid per second, you can use a syringe pump. It is called a syringe pump, and of course, syringe pump cannot operate continuously. When the syringe position, the piston position has gone from one extreme to the other extreme, you will have to stop and refill the syringe and again restart the thing and so on. There is also a positive displacement type of meter. The second one, the vortex shedding flow meter, it is noticed that if you have an obstruction like this in a flow, for example, I can have different shapes for the obstruction. The flow which comes from here, it gives rise to vortex which is shed at a known frequency at a certain rate. That means that if you look at the frequency at which the vortex are shed, it follows the relation which is given here. This is the Stokes number, which is nothing but the Fd by n, Fd by V, where F is the frequency of the vortex shedding, D is the diameter, frontal diameter of the body, and V is the velocity. So the Stokes number has a constant value in this range from here to here, and what does it mean? The velocity here is given by the frequency of shedding of the Kármán vortices which are developed at the periphery here at this corner and this corner, and that is given by the frequency of shedding multiplied by the diameter divided by the Stokes number. The Stokes number is a constant in that range, and therefore V is proportional to the frequency of the vortex shedding. If you are able to measure the frequency of the vortex shedding by just monitoring the pressure at the back, the pressure each time there is a vortex shedding, the pressure will go through a pulse, there will be a change in the pressure, and you can measure the number of such events and then find out how much time it took, and immediately I can find out what is the velocity. So vortex shedding meter is one of them which can be used for measuring the velocity, and this velocity is nothing but the flow velocity, average velocity of the flow. And the turbine tube flow meter, this is another meter which can be used. It is essentially like a turbine. So if a certain volumetric flow rate takes place from the left to right, the turbine is nothing but a device with blades on the periphery of a rotor, and the number of times it is going to rotate is proportional to the velocity of the fluid which passes through from this side to this side. It consists of a rotor, then the bearing to support, and also straightening vanes, so that the velocity is in the direction parallel to the axis and C is the reluctance pickup. Each time it rotates, the reluctance pickup will register by producing a pulse, and you can again count the number of pulses and per second and determine what is the velocity of the fluid through the turbine rotor. So basically with this we come to the end of our discussion on flow rate measurements, and in the next class, next lecture, we will look at the measurement of temperature in a flowing fluid. Some aspects of it we have not covered earlier, we are going to look at it in the next lecture. Thank you.